Good day, everybody. Today I want to look at finding the relative extrema of this multivariable function. And after we get the relative extrema, we'll note something interesting happens. But we'll wait on that for now. Alright, so let's get to work here. So to find the extrema, we'll solve for the critical points, which means solving f sub x equals 0 simultaneously with f sub y equals 0. Alright, so from f sub x equals 0, we get 5e to the y minus 5x to the fourth equals 0. And from f sub y equals 0, we will get 5x e to the y minus 5e to the 5y equals 0. So many ways to solve these two equations. I'm going to start with the f sub y one. So from this one, well, we get 5x e to the y equals 5 e to the 5y, divide by 5 e to the y, and we get x is e to the 4y. Just dividing by 5, canceling, divide by e to the y, it subtracts the power. Alright, so x equals e to the 4y is what we need for this equation to work. So now let's sub into the f sub x equals 0 equation, and what we get is 5 e to the y minus 5 times e to the 4y to the fourth power must equal 0. So this is the same as 5 e to the y minus 5 e to the 16y equals 0. And again, if I solve, I'll get e to the y equals e to the 16y. If I move that term over, divide by 5. And this can only happen if the exponents are equal, so y equals 16y, which implies y equals 0. So y equals 0 is needed for this equation to be 0 when we have x equals e to the 4y. So since x was e to the 4y, this implies x equals e to the 0 or 1. So 1, 0 is our only critical point. That'll be the only point that works on both equations. Let's label it. So the discriminant, so fxx is going to be negative 20x cubed. Fyy, be a little more involved, that'll be 5x e to the y minus 25 e to the 5y. Then minus fxy squared, well, that'll just be 5 e to the y squared. So the discriminant at 1, 0 is going to be negative 20 times 5 minus 25, so another negative 20, and then minus 5 squared, so that'll be 375. Again, the second derivative we see right above, whoops, at 1, 0 is going to be negative 20, so that means we're concave up. That means we're concave down, I mean. Oops. And so we have a local max at our only critical point. So it doesn't seem like anything too interesting yet. But the thing is, now this is not a global max. I guess I'll write that in. So not a absolute max for the function. The function is defined everywhere for all x and all y. Now this can't happen in one variable calculus. If you have a local max and it's the only critical point, it has to be an absolute max. If it's the function is defined, say, on the entire real line, right? You can't go up to have a max and then come back down. It has to be an absolute max, because how else are you going to get above it? If you try to get above it, somewhere else there'll be that second critical point, or critical value. But let's see here. So there's the local max. It's at 1, 0. The z value is 3, but there it is. Just go ahead and look at the graph over and over. Here it is with a point on the top and a horizontal plane at z equals 3, testing the tangency right there. And if we zoom out now, then we see it's not an absolute max. So we do get higher values farther away. But there's no other critical points. So there's no other places where both derivatives are 0. So there we go. That's the function. That's the thing that can happen with multivariable calculus, but can't happen in one variable calculus. A function defined everywhere, which has a local max, that's not an absolute max. Okay, so that's the end. Hope you enjoyed. Adios.